Okay, so we have already done oscillations, waves, and how to use a mathematical description. To describe mainly sinusoidal waves. And you guys know how to read, how to write, and how to express all the characteristics of particular kinds of waves. Very, I hope, not straightforwardly. And we have done a little bit of interference. Okay, that's what we did last time. So we sort of understand how when you have more than one wave meet at one particular point, you can just do the summation. It's a simple linear sum. So you just add those two together. We had the simple superposition principle. So this means 1 plus 1 equal to 2. So far, so good. All right. And I think you have done a lot. So what we are about to do today is closing the chapter about sounds. And so I think this is going to be something that I think just test your understanding of what we have been doing in the past couple lectures. And that will be, I think it's kind of a little fun project to do. I don't know, I'm calling it a project, but I don't think it's a project for you. The reason I say I would like to call this a project because instead of having you just sitting and listen to whatever I'm presenting to you and just, maybe ends up with like a formula or something, I think this is a good chance for you to try. Think of it like an application of what you have been doing with the describing the sinusoidal waves using sinusoidal function, plus applying the superposition principle and try to understand a phenomena that is actually very important and it's going to be very important later, well, in your life, maybe, or in your technological related stuff. It's actually, it's one of the main things that people utilize in a lot of technologies. All right. But anyway, before we get too far, so it's a topic, the last topic in this handout. As you can see, the slide is pretty blank. I don't have anything for you here except a couple of images over here, like a diagram and stuff. And the topic that is going to be the closing topics for this particular handout is standing waves, guys. Woohoo! So just introduce standing waves. And as the name implies, it must be a wave that is kind of standing. So it's like what we are about to experience is a particular kinds of waves that is so unique that it sort of like deserve a name for itself, the standing waves. Okay, so I'm going to use this as like a workshop and you guys follow my steps right here. Okay, step number 1, can you write down a sinusoidal wave equation that has wavelength lambda and the frequency f, amplitude a, traveling in the positive x direction? That's it. That's first step. So we're just going to apply the stuff that we have been doing so far. Well, I can't, no problem. I can do that. So let me call this y1. And just to remind you, this has to be a 2 variables function, of course, because we know the amplitude is already sitting in the front. And of course, you can pick sine or cosine, up to you. It doesn't really matter much in this case because we don't care so much about when it's going to start, because the information I'm giving to you is just lambda, the frequency, the amplitude, and the direction of motion. So I can just pick sine if I want. And then you can say, I know the lambda. So once I know the lambda, I can move on to k equal to 2 pi over lambda. You guys with me? Plus another thing that you know is the omega. Oh, I'm sorry. We start with the f. Okay. Frequency. Then you can say you can figure out the omega through the 2 pi f. So it depends how would you like to write down your equation. So I can write it like 2 pi over lambda x. Okay, and then I have 2 pi ft. And because it's running in the positive x direction, I pick the negative sign in between. That's it. Is it good?
Okay.
Okay, so far so good. Now, what I'm going to ask you to do is, what if I have another wave, exactly the same wavelength, frequency, amplitude, but it's traveling in the negative x direction? What would be your second wave? Go ahead, write it down. That it's not that grand. Okay, so what you can write down is just say, okay, let me call this wave number 2. Okay, same amplitude, same wavelength, same frequency, except it's traveling in the negative x direction. So I pick a positive sign right here. And that is it.
Okay.
Done. Okay, so far so good, guys. Cool. All right. You can always rename this, or rewrite this one as a K. You can call this omega, make it a little shorter if you like. They are the same. Everyone okay with that? Now, it turns out these two waves is traveling on the same medium, or in the same medium, or on the same string, or whatever, inside the same environment, or whatever. So what they are doing is, let's say if I have a string, then it means the one that is right traveling wave is just going, oh, let me color code it here. So the one is traveling to the positive x direction. The blue is traveling in the negative x direction. Okay. If it's a sound wave, then you can think like you have two sources of the sound that generate from different directions, and then they just sort of like send sort of like head on. So these two waves, the sound wave that coming from two sources, just sort of like going opposite directions and meet somewhere in between. Okay, my question is, find me the interference between these two waves. So what is the final total summation of these two waves, guys? That's it. Go ahead.
Okay.
Find me that. This is serious. This is like a workshop or something. All right. So give me the expression for the interference between these two waves. So in conclusion, these two waves is just exact same shape of the wave, but it's traveling in the opposite direction, and somehow they meet. So I want to find the interference between these two waves. 2x, okay. The 2x, what does it mean by 2x? Like twice as big? Is that what I'm guessing? All right. Twice. Okay, that's a good sort of like indication in terms of the maximum displacement. So that sounds correct. Yeah, it looks right, because this is the first figure that we started out talking about the interference there. So the scenario that we are looking at is something like this. That's what we sort of like started this topic with. I have y1, I have y2, but in our case, the amplitude are the same. So in general, what you're going to get is you're going to get twice as big as the amplitude, right? When they are sort of like separated. But I want the whole form. What I'm saying, the whole form means I want the whole function written out. Because don't forget, waves has to be two variable function. Woo. What about that? Oh, maybe I put it in the wrong place. I have some blank space for me to write it down. Oh, sorry. Okay. Okay, you guys write it down for me first while I'm moving this whole stuff here to a blank page. Okay, I think this is good. Copy. Okay. Ooh. Oh, okay. Ooh. Okay. Paste. Okay. There you go. Ooh. All right, just leave it there. That's fine. Sorry, it just not so. It's just doesn't seem to work well. This app is just it's not very intuitive at some point. Okay, so far so good. All right, so I think this is done. Okay, you guys got the expression? Oh, it takes a lot of time just to move this thing. Need to go to iPad. It's been, I have been teased about, but I think iPad is better than, okay, all right. I'm using Android for too long. Okay, so what is your final expression? So for those of you that's still like, okay, I'm not so sure how to proceed, don't worry. The idea is very simple. 1 plus 1 equal to 2. What else can you do? So we said that it's 1 plus 1 equal to 2. So it means the net waveform or the wave function, it has to be just the sum of those two waves. But then because you have a sinusoidal functions, all you need to do is just recall that trigonometry identity, just give it a shot. All right. And we saw that one before. If you slide back, there's a reference in here. We did it before here. There. When you have two sine functions added together, you have 2 cosine of the difference over 2, sine of the sum over 2 in the argument. Okay. So I'm going to just follow that. So what I can do is just saying that is going to be 2a. Okay, let me rewrite that identity here. Cosine of the difference over 2, sine of the sum over 2, just the average. This is what we're going to use. Okay, let's do it. Okay, so I have number 2 here. That's a factor in the front. I have a common factor a here. I pull it out. Okay, now let's attack the cosine first. So I take the argument, subtract them out, divided by 2. So you can see that the x disappear. You ended up with twice with the negative sign if you like, but that's okay. Omega t over 2. You guys with me? Okay, or if you don't like omega, I can just leave it as 2 pi f for now. 2 pi f over 2t. But the negative sign, you will see that eventually I can just get rid of it because cosine of the positive or the negative arguments give you the same value. Move on to the sign. I just add the 2 divided by 2. The time components will disappear because one is negative, one is positive. So you only left with just the x component. But then you have 2 of that divided by 2, you get original back. So it's just 2 pi over lambda x. Woohoo! And that's almost done.
Okay.
Sort of like, how do you feel? I don't know what do you feel, but at least that's just following just the straightforward summation between 2 functions. Let's rearrange this one a little bit, shall we? Isn't it just 2 pi ft in the cosine? Okay, let me see. Oh, you're right. Thank you. Yes, yes. Because it's a subtraction there. Thank you. Okay. Is it good? Okay. Okay. All right. Thank you. Yes, yes, yes. Okay. Just because you subtract out, you get double that and then divided by 2, everything back to original. Very good. Thank you. Okay. So what you have at this point is now, this is so cool, guys. The cosine has the t function in it. The sine has the x in it. Woohoo! Thank you. Okay. You have cosine that stick with the t. You have the sine that stick with the x. So it's somehow by doing this, you separate the x and t. It doesn't look originally like x minus vt or kx minus omega t anymore. It seems like it gets separated a little bit. And that's kind of nice. The reason I say it's nice because of this. If I rearrange this term one more time, okay, just to make it a little bit nicer. So I can write it like 2a. Let me pull that space portion of this function into the front, 2 pi. And let me write it 2 pi over lambda x. And let me keep that cosine toward the end. There you go. And this is the one that I want. Guys, look at this. This is still the function that is trying to describe the wave. But this is the interference between 2 waves that running in the opposite direction, right? Yes, yes, very good, very good. All right. Now, the cool thing about this expression is, if you look in the front. My question is, can you make this box, the blue box, disappear?
Okay.
Can you? Well, yeah, John, I can actually make this box go to 0 if you pick the good value of the x. I mean, the good value means the value of the x that actually just make this box disappear. How? You know the condition for the sine of the angle. Sine of something, let me call it theta, is going to be equal to 0 when theta is either the 0, the pi, the 2 pi, the 3 pi, on and on, right? So that means what I'm having right now is if the argument that I have here just perfectly make a multiple of pi, that point will give you nothing after the interference. Isn't that cool? Wow. Got that one? All right, let's give it like sort of like clear this thing up. So let's pull this one out. And let me say, so, oh, whoa, sorry. So 2 pi over lambda x. If it's equal to multiple of pi, that's when you're gonna get everything, no matter when, no matter what, no matter how long you wait, you get 0. So as long as you standing right here we go, pi cancel, n over 2 lambda. See, I just move things around and just I want to figure out where are those x's. That's eventually nothing is moving. This is the condition. Well, hey, Ajahn, if you are standing at the point where x is just multiple of half the wavelength, you get nothing. Whoa. Wow. All right. Nothing means nothing is moving. And now you start to understand why we want to call this a standing wave, because even though we already discussed that wave never stop, it has to move everywhere in the waves, has to oscillate up and down, up and down. However, when you have interference, and this comes from two waves moving in the opposite direction, you can create the condition where at these particular points, at these particular locations, the particle does not move. Okay, I'm just stopped moving. All right, it's not frozen internet or anything. Okay, that's a comment here. Probably yes, but I don't remember trigonometry. All right, don't worry about the trigonometry identity, that properties, that's fine. But that is the condition. That means as long as you are staying at this particular, that's this particular spot, multiple of lambda over 2, that will be the spot where there's no movement. So I can actually contrast this to the different condition for Ajahn. I can go the other way around. I can go to the maximum. So if you want to go to the maximum, you can say sine theta is equal to the max. When you say equal to the max or equal to the min, okay, I don't want to do the division here. So it's either max or min. That means this is going to be +1 or -1, right? That's the value of the sine theta. And that happens when theta is either pi over 2, 3 pi over 2, 5 pi over 2. So that means the sine theta will reach its maximum magnitude. When I say magnitude, mean it's just either positive or -1, and I don't mind. Then you hit this particular value when it's at 90 degree, 270, you add extra 180 to it, 540, on and on. Okay, is that 540? Yeah, well, 750, I don't know. All right, but anyway, in terms of pi, you just keep adding pi to it. You start from pi over 2, add pi to it, you get 3 pi over 2, 5 pi over 2. At this point, you will get the maximum oscillations from the particle in the medium. And what are these points? Once again, you grab this 2 pi x over lambda. You set it to the odd multiple of pi over 2. You remember the odd, you just say 2n. You can pick plus or minus 1, up to you. Okay. And then you do pi over 2. This will show you the place or the locations of x that give you the maximum value possible for the oscillation. So pi cancel. So what I'm getting over here is x equal to, okay, you look at this, 2n minus 1 over 2, 2n minus 1 over 2, and then you have pi over 2 here. So you have some, I mean, don't worry about the formula at this point, but that's all right. It's just the odd multiple of the half, oh, sorry, not the pi, half the lambda. There you go. Half the lambda. There you go. All right. So what you have over here is, it turns out you would like to get an odd multiple of lambda over 4 because you have 2 of the number 2 in the denominator right there. All right. So this is what you get for the maximum. Maximum. How much is the maximum? Because you already set sine theta to be -1 or +1. So over here at these locations, you get 2a oscillation. And that's what your friend just mentioned. Like you have the twice of the amplitude. So these locations, the particle will oscillate up and down twice as big as it's as compared to the individual wave. Sounds like a good one here. All right, so it might take like a long process to analyze what we are about. I mean, what we are about to do or what we are doing at this point. Okay. However, this is the conclusion that you are getting is there are some spots on the interference that nothing is moving, and there are some spots that actually travel twice as big. Okay, there's a question comes in. The formula still doesn't explain harmonic sound. Okay. It's coming. Harmonic sound is coming. Okay, so what you have here, it's actually easier than it looks. But what I am trying to do right here is just so you know that what you have already learned in the past week allow you to do this analysis. Isn't that cool?
Okay.
So it might not be that cool, but at least this sort of showcase how, I would say, simple. I'm not trying to use the word simple, but it's just a straightforward way of applying all the principles that you have learned. Okay, you learn how to describe sinusoidal waves, you learn the superposition principle, and you know that once you have wave try to interfere with each other, all you need to do is just add them up. 1 + 1 = 2. And then you apply some trigonometric identity. This is just popping up by itself. Okay, let's look at the conclusion. You got the formula, but in reality, the real application is actually even easier than this. This is what it is. I hope you now start to understand what is about to happen now. So this is the diagram that trying to showcase the standing wave phenomena that we just analyzed. Okay, when you look at this one, you might feel like I'm confused again what is about to do. So this is what happened. This is under the topic of sound. So that's why we have like a tube or something that sound can get generated in here and travel in and out. However, it will make more sense if you start this scenario using a wave on a string. So think about this. If you have a wave on a string right there, and then you generate a wave in it, oscillations, right? Sinusoidal waves. So at first, the wave probably just try to travel to the right. It's a sinusoidal wave. So it's going to keep traveling until it hits the end of this one. The wave will get reflected. We already discussed this one, and it's actually inverse the phase and on and on, but I don't care. So the thing is, the reflected wave generate the exact same wave, but traveling in the opposite direction. You guys with me? Okay. So after things continuously generated, the wave just keep traveling to the left and right, on and on. So at the end, so you having the situation that we just started out. You have two waves traveling in the opposite direction. Okay, cool. So with that in mind, then this is exactly what we had for the description of these two waves. And by looking at this, you will eventually see that some points on here, the particle will not move whatsoever. Not move, not move, not move. And there will be some other points that the particle just crazy, going up and down twice as big as before. So that's why you have this kind of sort of like a loop like looking waves, even though there's no way that you're going to generate a loop in a single string. But because the oscillation is so fast, then you will see like, you know, and sort of like a blur images and everything just look like a loop. Okay, so that is the stuff that we are looking at, is the standing wave, because there are some points on here that actually the waves just keep standing there. It doesn't want to move. That's it. That's standing, 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 standing. Okay.
Okay.
I don't know, you kind of like this one or not. But I hope it's clear up things about standing waves, but it's not so clear. Oh, and then, oh, thank you for this link over here. Okay, there is a simulation here that I would like to sort of like show you guys as well after understanding this. And oh, okay, if you click this link, I think this is a very good one. If you try the link that your friend just sent to us, I think that's good. All right, that's good. But actually, I have uh, uh, a more related one, but it's the same website. All physics over here is really good, actually. All right, guys. So you guys can go to, well, let me give you the link. It's at the same place, actually. Okay, you guys go to this place. Which one? Okay, guys, go to this one. All right, and then I'm trying to show you what is about to happen, not a wave pulse. All right, you guys go to this, and then I'm going to show you on the website here as well. So let's go there together. And this one is better understanding by exploring the animation. I think that's the best we can do. All right, so you have all physics. I don't have that link in here. .com. Am I? Wait, I should have that link in the Zoom, though, right? Where are the let me find out. I want to know. Where can I find the chat? See, I still don't know how to navigate this software over here. Oh, here, I found the chat over here. There you go. All right. All right, W10. Here we go. All right, so in here, you guys can play around with it. It's interactive, so it's very good. All right, and what you have over here is you can run it and you can check some options over here. Okay, and this is an air column, and you can pick between to have two ends open or just one ends open. Okay, this is exactly what you saw in the slide. So if we start from the two ends open, and let's try running it, you can change the length of the air column, whatever you like. You can change the wavelength of this one. Okay, but then the thing is, as you can see, it has some movement in here, but to run this is going to show you a little bit better idea. So this is a fluctuation that is going on in the air column. As you can see, it's not going to show up as a loop. Okay. However, if you imagine that if this fluctuation going up and down so fast, then you're going to see something like a loop. However, the good thing about this simulation is if you show the original wave on the top right there. So that is the wave that is traveling to the right. Okay. And then the good thing about this simulation is it's so good. I love this one because it's better than whatever the figure that shows up in the textbook. You can show the second reflection. I mean, let's go with the first first. Let's start with the first reflected wave. Here we go. See that? That's what happened right here. So the blue one traveling to the right, the red one traveling to the left, and the combination of those is underneath in the black. That's on in the lower column there. That is the sum. See that one? All right. And if you look at the position on here, if I can still annotate, I don't think I can annotate here, can I? Oh, here we go. I can annotate this. So if you look at this spot, if I can find it, see that? It doesn't seem to move after the summation. Oh, is that, I don't know, you're having fun with it. This is what it means by standing wave. But then what I'm going to try to show you is this. What if I change the wavelength? First, start with the wavelength. So I'm going to change the wavelength a little bit here. Once I change the wavelength, oh, I might have to stop it first, I guess. Can I? Okay, I can change it now. Okay, I'm going to change the wavelength a bit. Oh, I'm still under annotation, sorry. Oh, stop sharing, sorry. Oh, no. Wrong one. Okay, let me share again. Okay. Oh, what is going on here? Sorry, guys. Just chat. Okay, let's go there again. Did I lose it? Okay, let's reload. All right. I mean, but and you guys are supposed to play around on your own desktop or whatever tablet, on and on. Okay, let's run that. Okay, here you go. Show the first two reflection. There you go. All right. Now, what I'm going to do is I'm going to adjust the wavelength. You see something here? Okay, and then run. Can you see? Can you see that the resultant wave in the bottom, the black one, doesn't seem to oscillate that much anymore? So this is not a good wavelength. This particular wavelength does not generate a very high amplitude oscillations. You start to see something here. Okay, let me move things around a bit. Just adjust a bit. Okay, and run again. Oh, this is still bad. I'm just changing. Run again. Ah, that's better. All right, so this is pretty close to the maximum that is possible. So it seems like I can just keep adjusting this and run again. Oh, it doesn't work again. See, so there are some particular wavelengths that eventually you're going to be able to generate a very high amplitude oscillation, which we know the maximum possible is twice the individual amplitude A. But at some particular wavelength, it's going to be bad. You're not going to get that big of the interference. Okay, so you just have to keep sort of enjoying this, having fun. Try to adjust the wavelength and then run until you can see that there are some particular wavelength that you can generate a good shape of the oscillation. So this is exactly what is happening. The conditions that we need has to be the perfect fit for this particular length of the tube. So you guys sort of follow a little bit. So there are some sort of like a selections for some particular wavelength that works for this particular length of the loop. For example, instead of adjusting the wavelength, I can adjust the length of the tube itself. For example, I can just squeeze this tube down. Oh, not good. Not so good. We just keep slide it down again. It's a little bit better. See that? It's a little bit better. I think I can do a little bit better there. I'm just keep adjusting. Oh, that's getting bigger and bigger. See that? Getting a little smaller. Run again. Oh, that's even better. Okay. Keep going. Get it shorter. Already. Wow, it's almost hit. Yeah, something like this. So there will be some particular relationship between the length of the tube and the wavelength of the wave that is traveling inside that eventually is going to generate the maximum oscillations in the medium. Okay. Sound engineering at its core.
Okay.
Yeah. I like that. So that's the whole thing. It's about the musical instruments and all this stuff is right here. So that means there will be some particular wavelength. And of course, when you talk about wavelength, it means some frequency that is going to be very, very good oscillator that's going to oscillate really well in here. And that will be the frequency that you will hear out of this tube. And this is the reason why when you have a musical instrument, the one that has like a tube like this, for example, like organ, like the big blowing stuff that has different length. I don't have it with me. I cannot find it. But the idea is this. That's why the pipe, the organ pipe has to have a different length because each length will correspond to different notes. And the reason that you have to cut the pipe at particular length because you want the frequency coming out at that particular note. You cannot pick other length because other length will go to a different frequency and then you won't get the notes that you want. Like sounds like a good one. Okay. So same thing with this. So everyone can play around with this. I don't know if you can play with this or not. But when you have a straw or you can pick a straw and then you blow at it, you hear the sound coming out of it. That this note right here is because of the length of this straw generate this note. Okay. Now, oh, I forgot. Let me bring the scissors. Just a second. All right. So this one you can just play it at home. Here, there you go. I don't know, can you hear it or not? But what you can do is, I'm gonna cut this shorter. That's my straw right here. So if I cut it shorter, what do you expect? Just remember the notes here. Okay, I cut it shorter. Can you hear that? Okay, I can cut it shorter. Okay, you can just actually, if you do it yourself, it's going to be a lot more fun. You just blow at it and keep cutting it. Oh, I don't want to cut myself. See that? So it's going to get higher and higher pitch. And this is the reason why if you fill up a bottle of water, okay, if you have a bottle of water, then every time that you fill the water in here, you will hear the noise like, you know what I'm saying? So that's what it is. So the reason at first you see a lower pitch sound because the air column in the empty bottle of water is just so long. It's a whole bottle. Once the bottle start to fill in, then the water is just to rise up. Then the air column in there getting shorter and shorter. So it's the same thing as you have the tube that has a shorter length. So that's why when the level of the water is rising up, then the air column is getting shorter and shorter. So the frequency that you hear is going to get higher and higher pitch, just like what you just saw in the straw experiments there. So that's why every time you fill up a water in a bottle, then you see it like it's just the pitch is getting higher and higher. That's what it is. Okay. All right. So I hope that
Okay.
give you an idea that actually that is a standing wave in action. Actually, you can experience that all the time. Okay. And you can compare the straw doesn't really matter what shape of the straw. When I say shape, it means whatever the cross section, the radius, and other stuff. I don't care because all you care is just the length of the straw. So you can go and grab the straw from one store, go to the next cafe, and go to the next coffee shop or whatever. As long as the straw having the same length, and you blow at it, you're gonna generate exactly the same frequency. That's how natures work. All right.
Okay.
All right. So I hope that's kind of mixed. It's a little dirty here, but that's all right. So this is the key that everything that you are hearing over here is just the picking, or you can say selecting the correct wavelength or frequency, depends on what you would like to talk about, that match the shape of the tube. It doesn't have to be just only the tube, actually. It could be wave on a string or whatever. So let's come back to our discussion a little bit. Almost done, guys. In reality, the way that you calculate things is going to be quite simple. Okay, let's do this. Okay, so what you have is this. Now, the way that you can actually do is just give the good condition for the wave to travel in a tube. Okay, let's start with this because this is what we did, right? One end open, the other one closed. So you have a tube with one end open, one end closed. So the key is, you know, that the wave in the tube is a sound wave, and the sound wave is just the oscillation of the particles. At the closed end of the tube, the molecule just stuck on the wall, cannot move. There's no way that this is going to be able to travel. So this is a perfect fit to put a place where the particle standing still. This is the place. This is it. We love it. And we would like to call this a node, the N. N is node. So the node is those locations that the particle does not move. That is the standing positions of those particle. All right. And now if you look at the open end of this one, okay, the air molecules here can travel up and down. I mean, not left and right in this case, left and right as much as it can. So this is going to be the perfect fit that you will place the position where you have 2A, twice the amplitude. Here at this point, this is going to be the point where the molecules can oscillate as big as it gets. So we're going to name this one A, which is the antinode. And that's it. Once you fit these conditions, all you need to do is just, wow, if you look carefully with our analysis over here, it turns out every position where the waves particles is stationary, they are going to be separated by half the wavelength. Can you see this factor here? You jump every half of the wavelength to get to the next antinode. Or if you look at the node, I'm sorry, I said antinode, node. So one more time, sorry. So you have to travel half the wavelength when you want to go to the next node, because you adjust the n by one, right? 1, 2, 3, 4, 5. You get to the next node by moving half of the wavelength. Actually, same factor shows up here, lambda over 2. So if you want to go from antinode to another antinode, you have to travel half the wavelength. So that is the suggestion that it turns out the distance between nodes or the distance between antinodes must be half of the wavelength. And this is how easy it is to work on this one. Here, look at this. The second figure actually works better. So if you have a loop, which now everyone understand that this loop doesn't mean that you have a wave split into two directions or anything. It's just the combination of wave that travel in the opposite direction. Okay, it's oscillate up and down, just like you saw in the interactive simulation there. Then this is the distance between the node to another node. And we know that this is going to be half the lambda. That's it. Done.
Okay.
I can actually draw this one a little bit further, and then it will clear things up a bit. Because when you look at a node, it's actually half of the cycle. Of course, why not? So actually, that is another lambda over 2. So the separation between the antinode is going to be exactly halfway of those nodes, and it's going to be separated by lambda over 2 as well. So that's so easy. In conclusion, you can actually throw away all the analysis here. So that's somehow, I mean, I can teach you like that. It's like, hey, guys, just remember this, but that doesn't make any sense, right? Just memorizing the formula. So I think you understand how things goes now. So the key is when you look at this first conditions over here, well, Ajahn, I set the node right here. I set the antinode right there. That is half of a loop. You guys with me? So now I can tell you right away, this length of the loop, length of the tube is going to be the length of half of the loop. But everyone now knows that one loop is half of the wavelength. So it's going to be 1/2 of lambda over 2. So it's lambda over 4. So you know exactly that if you choose the wavelength to be 1/4 of the length of the tube, that's when you get the first standing wave. All right.
Okay.
Sounds cool. And just to prove that this is good, I can actually bring you back here. You notice this? You look at the column, the air column there is 2 meter. And the wavelength that you are looking at over there is about 7.7, even though it's not perfect just yet. But that's about lambda over 4. So just to make it, okay, let me cheat a little bit to make, let me put 8 in there. So if I have a wavelength of 8 meter, what kind of tube should I pick to make it fit perfectly? Okay, lambda over 4 is going to be 2. So I should pick 2 meter air column. All right, I can get this close. Okay, this is close enough. And that's when you're going to get the highest oscillation. Can you see that? Okay.
Okay.
And if I just accidentally pick like weird length, let me pick like, okay, maybe 3 meter something. See, oscillation looks ugly here. You're not going to get a lot of sound coming out of it because the amplitude of oscillation is so low. Okay. And then eventually, if you keep doing this, then you can find out that you're going to be able to find other wavelengths that match these conditions. What are the conditions? The right portion has to be the nodes. The left portion over here has to be antinode. So what you can pick is you can say, Ajahn, I can do one more twist. If I twist one more time, I'm still started from the antinode, ends up with the node. I'm still okay. I should get another perfect standing wave as well. So if this is the case, well, that's good. So the length of the tube is 1.5 loop. 1.5 loop. Okay, I can write 1.5 loop to be 3/2. One loop is lambda over 2. So it's going to be 3 over 4 lambda, or 3 lambda over 4. Just make it like that. Okay, 3 times the lambda over 4. Sounds good? Not bad, not bad. And about Ajahn, I can do one more twist. So I want to do double twist here, bam, bam, and then it will just ends up with the nodes. So if this is the case, you get 1 loop, 2 loop, and a half. So the length of the tube is 2.5 loop. Okay, and that means it's 5/2 of lambda over 2. And that is a 5 lambda over 4, on and on. So that means at one particular setup of your tube here, you can get multiple conditions for the standing waves. And that's where the harmonics come in, guys. So the frequency that you hear here is not a single frequency. It turns out there is something going on in here, like more than one way that you can actually fit the sound wave in this tube. And whenever that you hit these conditions over here, you always get some standing wave. So the sound will be loud. That's what you're hearing. Okay. So in conclusion, you can call the first conditions that you can meet here, the easiest case, the lambda over 4 case, to be the first harmonic. Okay. And now you can see that when you want to go to the next frequency, you have to triple that, twice the original. So this is 3 times the frequency because everything is just triple that one. So what you have over here is the frequency will be triple as well. That's why you get the third harmonic right there. And when you go to the next frequency, now you can see that you're going to have a 5 times the original, I mean, the first harmonic. So this means the second possibility is when you get 5th harmonic, on and on. So you can have a conclusion in the case of one open, one closed tube, that the harmonic or the frequency that happens in here, it's going to be just the odd multiple of the first harmonic. Okay, sounds good? I mean, I don't know. Okay. And the easiest condition that you can find yourself in the standing wave condition over here, we call it the fundamental. It's fundamental frequency. Okay, so that means for the case of one open, one closed, you have only odd multiple of the fundamental frequency there. Okay, sounds like a not too bad now. All right, so let's use this trick and do this one with this. If you have just like an open tube, just like the straw that we just did the experiment with, these two ends are open. All you need is just meet the conditions. What are the conditions? The left supposed to be antinode, the right end supposed to be antinode as well. And all you need to do is just write the wave in there that fit this. So the only way that you can do it is just, all right, I have a node in between. That's the easiest, I mean, the lowest number of twists that you can introduce in the tube. So this is going to give you the fundamental frequency. But when you look at this one, Ajahn, the length of the tube is exactly one loop. Okay, all right. A loop is lambda over 2. So that's it. So you know the lambda. Okay, so I can write in terms of lambda, just change the mood here. So the lambda for the fundamental frequency or the first harmonic is 2L. And if you want frequency, it's just V over lambda. It's just V over 2L. Sounds good? Okay, and then you keep doing it, but John, I can do one more twist for you, but at least you still have the same condition of starting with the antinode, ends with the antinode, but I get extra twist. With that, you get 2 loops in there. You can count. So in that case, the length of the tube is 2 loop. So that means it's 2 of lambda over 2. So that means your lambda is 2L. Let me put it like 2L over 2. I just like this, I mean, sort of see the progression of the numbers here. So the frequency is just going to be V over lambda, and it's going to be 2V over 2L. Okay, I just keep the ratio like this because I just want to show you one more twist over there. All right, I'm still starting with the antinode, ends with the antinode, but with just one more twist. So what you have here is the length of the tube is now going to be 1, 2, and 3 loops. Okay, oh, okay. So when you have that, then it's just 3 times the half of the wavelength. So the wavelength is now 2L over 3. And the frequency is going to be V over lambda. So it's going to be 3V over 2L. That's the reason why I keep the numbers 2 and 3 on here, because that's what we're trying to compare with. The fundamental frequency is V over 2L. That's your first harmonic. The next frequency twice as that, 2 of that V over 2L. The next frequency is 3 times that. So for the open tube like this, what you get is the fundamental frequency will be this, but the next harmonic is going to be the second harmonic. So now I hope you understand the terminology here. The harmonic actually is just giving you the multiples of the fundamental frequency. In this case, you get twice the frequency of the fundamental. You call this a second harmonic. The third one is a third triple of the fundamental frequency. So you call this a third harmonic. Sounds good? All right. And that's
Okay.
pretty much done. It's taking a little bit longer than expected. Sorry, but I hope that's clear up this portion of the standing waves. And then I think you are done. Okay. Just on passing, there might be another terminology that people throw in. If we stick with the harmonic, it's just a frequency. But you might be able to call this the first overtone if you want. So it's the next tone. So if you don't care about the frequency, you just say, hey, what is the next possible frequency generated? That's going to be over of the fundamental by one step. So that this one is going to be second overtone. Okay. All right. So you can use the overtone terminology everywhere if you like. You can call this third harmonic to be first overtone in the case of one open, one closed too. Okay. And this one is going to be your second overtone. All right. So it depends on how people will mention about the possible harmonics or possible overtone. Depends on how they like to speak of different frequency. Right. With respect to the fundamental frequency, of course. Yeah. Sounds good?
Okay.
All right. So I hope this give you a conclusion of what we have over here. So let's take a break right here. After the break, I will show you how to solve these two exercises. And then I think that's done for this handouts right here. Okay. All right, guys. Take a quick break and we'll see you in a bit. Yeah. All right. All right. So if this is not too bad and I think you grab some idea behind this one and then I think we should be able to attack some problems here. All right, let's give it a shot and see how easy it is to apply to the actual problems. Okay. So a section of a drainage culvert, 1.23 meter in length. So there's a tall by Namsia. It's 1.23 meter in length. Makes a howling noise when the wind blows across the open end. So this is exactly just like what we did with the straw experiments. Exactly the same. So every time now that you can see like a tube, an opening, it doesn't have to be in a circular shape. Right? It doesn't have to be like a circular cross sections or whatever. It could be any opening, anything. But the sound is just complicated. That's all. But the idea is pretty much the same. So part A, determine the frequencies of the first three. They want the first three harmonics. So every time we see the words harmonics means we would like to talk about its frequency. All right. So what are those frequencies that going to get generated in this tube? So if the cylindrical shape is in the and open both ends, so we assume the shape of this one is just going to can be described using just open tube ends. So take the speed of sound to be 343 meter per second. Okay, so what are the first three harmonics, guys? Okay, so that's kind of like, okay, it's like playing games here. We already have open at both ends tube here. So we assume that the conditions that gonna meet is when both ends represent a position of an antinote. Okay, sounds good. So all you need to do is just draw the shape of the wave in this tube to match these ending conditions, or you can say it's the boundary conditions. So the easiest one that you can do is just doing the one twist over here. And then you can just do on both sides. I try to use a different color just so you can imagine that it's actually a real fluctuation here. All right. Even though in the case of sound, there's nothing fluctuating. It's not like a wave in a string that you can see the fluctuation of the string itself. But this one is an oscillation back and forth of the air molecules. Okay. But at least this is the representation that we can use. And this is going to be your first harmonic. or this is the lowest frequency that you're going to get out of this. This is your fundamental frequency. So this is your first harmonic. Okay. Oops, sorry, harmonics. And this is your fundamental frequency. Cool. All right. And the way that you can calculate its frequency, you can start by finding out what is its wavelength. Because you know the length of the tube, and you know that in this particular setting, it's half and a half of the loop combined. So see that? This is what? Loop over 2. This is loop over 2. So you have 2 halves of the loop. So in this case, you can say that the length of the tube is exactly 1 loop. But now we understand that the length of a loop is half of the wavelength. And that leads to lambda to be twice the length of the tube itself. And the frequency is just the speed over wavelength. So you can now substitute the numbers in here if you like, or I can just rewrite this one first. Okay, so the lambda is 2L. So now the speed of the sound is known. The length of the tube is known, and that's it. You get the frequency out of this. Sounds good? All right, and of course, you can always refer to this diagram over here if you want to just check out the formula for it. So it's going to be V over 2L. Perfect. All right, but for me, I don't even have to memorize anything pretty much. I mean, well, it might be faster if you can memorize things, but no need, right? It's not necessary. Okay, try again. So the next harmonic is just the one that just, give a little bit more work. You do one more twist here, but you have to start from antinote, and then you have to end up with the antinote. That's what you want. Okay, but that's all right. The calculation is still fine because now the length of the tube is going to be 2 loops. Yeah. Half, and 1. So this is loop and a half, and 1 loop. So 2 loops overall. And each loop has the wavelength over 2 length right there. So in this case, your wavelength is going to be just the length of the tube itself. And the frequency is going to be V over lambda, and it's going to be V over L, and it's going to be just 343 over 1.23. The whole thing is in the unit of 1 over second. However, if you recognize that, hey, Ajahn, because this is an open tubes on both ends, the next harmonic, yeah, if you refer to this one, it's like, oh, okay. The next harmonic is going to be the second harmonic. Or in the case of the both ends open tube, the harmonic is just multiple of the fundamental frequency. So you get all of the integers numbers relative to the fundamental frequency. So you don't even have to draw another figure. You can say it's going to be twice the fundamental frequency right away. All right. So after you sort of like familiarize yourself with this standing wave calculation, then you can just say, okay, when the tube is open at both ends, then the next harmonic is going to be double that. And for the next harmonic, the third one, oh, I ran out of space here. All right, let me squeeze in here. So you just do one more twist. There you go. Yep. All right. And now you can conclude that the frequency of this one is going to be 3 times. So for the fundamental, let me put number 1 in it. Okay, sounds good. So it's going to be 3 times of the fundamental frequency. And I can call this third harmonic. So I can just put the subscript in there if you want, just to say like, hey, the third harmonic is going to be 3 times. But this one after the fact that we know what is going to be the final answer anyway. All right, so this one is going to be 3 times the F1, which is already known right here. So we can just plug it in here. There. Okay, and then you can name this one F1 if you want. Does that make sense? Not too bad, I hope. Oh, I forgot to turn on the video. I was just hearing myself. All right. Okay. So is it good? Not too bad. Okay. So I think all you need to do for the standing wave in an air column here is just matching the boundary conditions. That's all you need to do. Okay. And in the case of open at both ends, you just make both ends to be antinodes. And then you just draw whatever the loop that meets the conditions at both ends. And then you're good to go. Okay. Sounds good. Not too bad.
Okay.
Let's do one more. All right. Just to double check that you guys sort of okay with this whole thing. Okay. Last one, guys. What are the, whoa, it's the same problem though. What are the three lowest natural frequencies of the covert if it is blocked? Oh, okay. So if it's blocked at one end, so now you want to turn your attention to one open, one end, one closed, two. Okay. All right. That's a question comes in. Do we always make both ends antinode? Here we go. So look at this case. It depends on the setup. In this case, they say one end is blocked. So that means in this case, so you're going to have one open end and one closed end. Does that make sense? So with this, you're going to get antinode on the open ends and you're going to get nodes in the closed end. Okay. And in this case, the fundamental frequency is the one that's going to go easy like this. All right. I do two sides of this one. There you go. There you go. Is it good? All right. So in this case, your fundamental frequency, let me call it F1, or let me start from the lambda first, right? So what you can say is now the length of the tube is going to be, now this is only half of a loop. So it's going to be loop over 2, and that is going to be half of the wavelength. Okay. All right.
Okay.
And that give you lambda over 4 to be equal to the length of the tube. And from here, your wavelength is going to be 4 times the length of the loop. And that allows you to calculate the frequency to be V over lambda 4L. And then you can mark this one as a fundamental frequency. And that's it. You're done. Okay, cool. Now, I mean, if you don't want to go back and look at the diagram and whatever, you can just keep doing it by give it one more twist, keeping the conditions at both ends to be antinode on the open ends and the nodes on the closed end. And then you just put it one more twist there. There you go. Oh, that's bad looking. There you go. Cool. All right. And this one, the length of the tube is going to be loop and a half. So it's going to be 1.5 loop. And it's going to be 3/2 of lambda over 2. I'm just sort of redo everything one more time. So it's going to be 3 lambda over 4. Okay, so the lambda is just 4L over 3. The frequency will be V over lambda. It's going to be V over 4L. And then I just put 3 in the top right there. But this matched perfectly with what we already analyzed, because you can see that the V over 4L there is exactly the frequency of the fundamental frequency up there. And this fits perfectly that from the knowledge that we have already built, it's triple the fundamental frequency. Yeah. All right. So this is going to be your first overtone. So the 3 lowest natural frequency for the one open, one closed ends tube, the next frequency will be triple of the fundamental. So this is your third harmonic right there. Okay. And then we can draw the final conclusion for the next natural frequency that you're going to hear from this one is you just add one more twist to it. All right. So it's still fitting the left open ends to be antinode, the closed end to be a node. And then you don't even have to do it one more time, because from the progression of the numbers, you know that this is going to be frequency is going to be 5 times the fundamental frequency. You can name this fifth harmonic or the second overtone. And that's it. You're done.
Okay.
This is not too complicated, and it's kind of like it's like playing games a little bit. All right, but this game has the restricted, conditions that you just have to meet. If you can meet that conditions, then that's it. You solve the puzzle. Okay, so does that answer your questions? We not always make both ends anti-node, right? It depends on the conditions of that system. Okay, just to make like a good contrast of this one, and I hope you can sort of like understand the whole sort of like story of this one is, okay, let me add a page here, and I'm going to ask you the final question of the day. Okay, so now, even though we're talking about sounds, we did some experiments with sounds, but what if I have a string back in the mechanics? So we started out like this, yeah? And I sort of pin the two ends of the string. A piano string, yeah, perfect, yeah, that's fine. Exactly right. And then this is the same thing as a piano, is like a guitar. So everything as a string instrument, you have this kind of setup. And then, of course, I can generate waves in here. So I can just plug the string, and it's just going to generate waves. What will be the frequency that you're going to hear out of this? And then you can apply all the stuff that you just learned, Ajahn. You already fixed both ends of the string. So this ends will not be able to move. That must be a node. This ends also cannot move. This must be a node. With me, guys? And that allow me to say that the first case that you're going to get is this, from node to node. Okay, and I'm going to use different color as usual. There you go. So if you know the length of the string over here is L, this is one perfect loop. So for this particular case, the length of the loop is just the length of the string itself. So the length of the loop is equal to the length of the string. L is equal to one loop, and it's just lambda over 2. So from here, the lambda is 2L, and the frequency is going to be V over lambda. It's going to be V over 2L. And then you can calculate the frequency that you're going to generate from this string. Isn't that cool? All right. No, that's not the right one.
Okay.
All right, and if you want to get this next harmonic, okay, in this string, so all right, just do one more word and twist, give it one more twist there. That's what you're gonna get. Oh, that's bad looking. Okay, here we go. There. So you start from a note, you ends up at, oh, that's kind of off a little bit. All right, let's end up at the note right there. Okay. So in this case, the length of the string is 2 loops. So it's going to be 2 times L over 2. Perfect. It's a lambda. So that means frequency is just V over, oh, sorry. It's just V over L, or V over lambda, and lambda is equal to L, and that's it. Okay. And then, of course, you can rewrite this one as 2 over 2. The reason I'm writing like this, because I just want to do some analysis, but John, this is fundamental frequency. That's the lowest frequency you can generate from this string. This one give you twice as that. So if you want to call the first one to be your fundamental, I put subscript 1 in there. This is going to be your second harmonic because the frequency will be twice as big. Okay, and now you can guess if you want to do one more, the progression is going to give you some, you already got a clue already. You twist one more. There you go. And now that is 3 loops. You still start from the note, ends with a note. So the length of the string is 3 times the length of the loops. And now is 3 lambda over 2. And then you probably can guess now the frequency you're going to get to be 3 times V over 2L. Cool. All right. And it's 3 times the fundamental frequency. So you can call this third harmonic. Ooh, there you go. And it's done.
Okay.
Okay. All right. And I hope by learning this standing wave in the air columns, You can actually apply this one to standing waves in any mechanical system. Like I'm showing you right here is the standing wave in a string. It works the same way. Okay. So there's a question comes in, how does this have to do with the tuning of musical instruments? Okay. The tuning of the musical instruments is just saying that the conclusion that I'm going to make right now is this. So in the end, if you have a string of length L, okay, and because in general, the fundamental frequency will be the frequency that you hear the most, because it's the easiest one to make, and it's just it's like the components of this one will be the highest. So as long as you keep the length of the string fixed at value L, you will always generate this frequency. See that? Cannot change it. Cannot change. The only way that you can change the frequency is you either change the speed of the sound, which you probably won't be able to change it because it's traveling in the air, except there is some change due to the temperature, whatever. But I mean, overall, the speed of sound in the air is pretty much the same. And because you're not going to change the length of your instrument, so it's always give you this frequency, no matter when, no matter where, no matter you want to play it at whatever point in time, doesn't matter. You're going to get the same frequency. That's why I'm going to sort of like conclude this lecture with this word. It's natural frequency. Seriously, guys.
Okay.
This is serious. So that means an object, system, that particle, or whatever that has something that is in oscillations will have its own frequency. And usually, as long, well, not usually, most of them and all of them, as long as you don't change its physical characteristics, you won't change. If you do not change any physical parameters, the shape, the size, the environment, whatever, the frequency will be stuck with you. Cannot change. And this eventually will lead you to resonance in the future. I don't know in this course or not, but the idea is your arms, your legs, if you sort of like free your arms, okay, and then you sort of like move your shoulder around and then let your arms just hanging there, it will oscillate at one particular frequency. You cannot change it. The only way that you can change it, you have to probably contract your arm in, move your arm in, out, or whatever, change it until you get the new frequency. Okay, so this is the reason why you can see a little bit for people that has a long legs seem to walk slowly, because the longer leg, the frequency is small, it turns out. But for people that has a shorter legs, like maybe like some mouse, like hummingbirds or whatever that is small, the natural frequency is high. So those mini, animals and stuff tend to move quickly with respect to like giraffes or whatever, super long, and they sort of like move things so slowly because the natural frequency seems to dictate how they behave, and that cannot be changed as long as their physical parameters are the same. Sounds good? All right. So just, take home terminology of the day is everything has natural frequency. And then you can manipulate with this a lot of stuff. Okay. All right.
Okay.
That's why bird chirp is so cute. Actually, bird chirp is as rough as dog bark is. Yeah, because yeah, the physical stuff of the birds kind of small, and and then the frequency comes up kind of like higher pitch, and then the dog is like bigger. Their pipe is just bigger, so the sounds come out differently. Yeah. So they went on the wall. All right, but that's all right. That's all right. Of course, the nature works that way. So yeah, I would say agree. Yeah. And because of the physical parameter of the vocal cords and all the air canal and whatever, That's why women tend to have a higher pitch sound than the men. The men is lower tone, lower pitch, and the women has a higher pitch because of the physical shape of their vocal cord and their pipes and everything. Yeah, so they cannot change. The only way that you can change, you have to contract. You know, if you want to make like a higher pitched sound, then you have to squeeze your mouth. You have to squeeze your whatever neck a little bit and stuff like that. And if you want to make it like a lower tone, then you have to, you know, stretch out a little bit, you know, change your physical shape of your pipe, stuff like that. Okay, sounds good. All right, guys. So I think that is it for today. And I think that's conclude this hangouts right here. So we have one more topics left to cover in this second module, which is about another kind of waves. It's light. Okay, however, we're going to look at the light from the perspective of their traveling light, just like directions. So we're going to learn their geometries, how things goes, and we don't want to do the sine and cosine anymore. I think that's pretty much enough. Okay, and to do sine and cosine for the light waves, we need electromagnetism theory. So that's why we don't want to do it there until we study electricity and magnetism. All right, so let's wait for it. Okay. All right, so I think that is it for today, guys. I think that's
Okay.
I think it's good. It's kind of like do things along together. It seems like you see how things get done together and anything. I hope this works. All right, guys, take care. I'll see you on Wednesday. Yeah.
Yeah. Question.